Dear colleagues, with your permission, I present our research, Intelligent Controller of Helicopter Turboshaft Engines Gas Temperature with Compensation of Transient Process, Inertial Delays and Optimization. The evolution of the aviation industry is tightly linked to advanced helicopter operations, which necessary sophisticated automation control systems incorporating sensor sets and visual devices to manage both manual and automatic control, especially in maintaining critical gas temperatures in front of the compressor turbine for optimal efficiency and reliability. The relevance of this advancement is underscored by the stringent and often conflicted requirements for modern helicopter turboshaft engine automatic control systems, is demanding high static accuracy, rapid response, and minimal stabilization time, which continue to drive innovation in multifunctional automatic control systems technologies under diverse flight conditions. Non-helicopter turboshaft engine automatic control systems which adjust fuel consumption using input sensors, compression elements and actuators suffer from reduced stability margins and permissible gain factors prompting the use of selectors, correction links with differentiators, and intelligent components to improve static and dynamic accuracy by compensating for sensor inertial delays. The research aims to develop an intelligent gas temperature controller that employs adaptive algorithm and corrective links to dynamically optimize control parameters, thoroughly enhancing stability, minimizing overshoots and reducing engine stabilization time across various operating conditions. The proposed controller is based on a double summation circuit that compares signals from thermocouples and a gas generator rotor speed sensor using an inertial link, a compression element, and a nonlinear unit to adjust fuel consumption, thoroughly compensating for turbine heating delays and stabilizing the temperature regime. In integrated adaptive algorithm and corrective link with differentiator to dynamically optimize control parameters in real time by adjusting gain factors and inertial link time contents, predicting temperature trends, and synchronizing system response to minimize transient fluctuation. Additionally, the controller features an adaptive control module between the summing amplifiers and the control channel selector, an adaptive differentiator in the measuring circuit for preliminary signal processing, and a transient mode monitoring unit connected to the actuator for feedback, ensuring that discrepancies between specific and actual parameters are eliminated to enhance overall system reliability and efficiency. The developed method utilized an adaptive observer with state prediction to compensate for inertial delays in gas temperature control, enabling accurate tracking of the desired temperature trajectory. It dynamically adjusts control parameters in real time through adaptive loads and future refines delay estimates with a neural network module. This integrated approach enhances system stability and transient performance, ensuring optimal regulation of engine conditions under varying operating scenarios. The developed neural network is a deep, fully connected feed-forward model designed to approximate the output function that corrects the estimated inertial delays by adjusting the base delay value. Its architecture comprises an input layer that processes the future vector, two hidden layers with nonlinear activation function, and a linear output layer that produces the correction value used in the control scheme. The network is trained on historical data by minimizing the mean square error using gradient descent and backpropagation therapy, enhancing the accuracy of system state predictions and overall control performance in the presence of inertial delays. The obtained results demonstrate that the proposed two-channel intelligent control exhibits distinct dynamic behaviors in its individual loops, as evidenced by the Nyquist diagrams, where one channel gas temperature remains stable while the other rotor speed is unstable. Additionally, the transformed amplitude phase characteristic diagram indicates that oscillation around 1.96 Hz are possible, confirming the theoretical prediction of dynamic oscillatory behavior under specific conditions. The obtained modeling results illustrate the transient process of gas temperature control in front of the compressor turbine. Left figure shows the system's response without correction link where a delay in selector switching causes a temporary surge in gas temperature. Right figure demonstrates an improved dynamic response with correction links, ensuring more accurate temperature regulation without exceeding the specific mode. The neural network consisting of two hidden layers was trained using the Adam optimizer and achieved an accuracy of 99.5 with a loss of 0.5% after 100 epoch. However, future training led of our fit in reducing the model's generalization ability. The predicted delays value closely matches the actual data with a determination coefficient value of 0.97, and the confidence interval approach was used for account for uncertainties in predictions. This figure illustrates how delays values vary with frequency from 1.9 to 2.1 Hz, highlighting a pronounced oscillation at 1.96 Hz that may indicate resonance of unique dynamic behavior. The use of the neural network effectively reduced delay by modeling complex nonlinear relations and prediction optimal control modes, resulting in delays not exceeding 0.016 seconds, a 36% improvement compared to the scenario without the neural network. This adaptability leads to a faster system response and stabilized operation in critical frequency ranges. The conclusions are presented in this slide. Thank you for attention.